Compute the divergence of the given vector field. So looking at this given vector field here, it's kind of a nasty function. So what I'm going to do is actually separate our given vector field out component by component, right? Because we know we're working with a vector field f in R3. So we know it's going to have an f component, a g component, and an h component. So let's think about each of these individual components and take their partial derivatives to help us get the divergence. So first things first, we have the f component. So our f component here is defined as x all divided by 4 plus 3x squared plus y squared. So here we want to take the partial derivative of f with respect to x, and you can either do this using a quotient rule, which I'm going to do here, or you could use a product rule. So using the quotient rule, this is going to be 1 plus 4 plus 3x squared plus y squared minus x multiplied by the derivative of the denominator with respect to x, which is simply 6x. And this is all divided by that denominator squared. So we have 4 plus 3x squared plus y squared squared. And simplifying, this is 4 plus 3x squared plus y squared minus 6x squared, all divided by, so nothing has changed in our denominator, that's still 4 plus 3x squared plus y squared squared. And we have two like terms here that we can combine. We have this 3x squared and a minus 6x squared for a beautiful final answer here of 4 minus 3x squared plus y squared. And this is all divided by the denominator 4 plus 3x squared plus y squared squared. And again, although these terms look similar, I want you to note that in the numerator we have a minus 3x squared, and in the denominator we have that plus 3x squared. So we can't cancel any terms, and so this is our final answer for the partial derivative of f with respect to x. So we need to do the same thing now for g and for y. So part 2, not y, excuse me, g and h. So g here, our g component, is defined as y, and that's all divided by 4 plus 3x squared plus y squared. And we want to now take the partial derivative of g with respect to y. And again, you can either use a product rule or a quotient rule. Pick your favorite and go. So I'm using the quotient rule again, so I have 1 multiplied by the original denominator, 4 plus 3x squared plus y squared minus y multiplied by the derivative of the denominator with respect to y, so multiplied by 2y, all divided by the denominator squared. So 4 plus 3x squared plus y squared squared. And we want to simplify. So we have 4 plus 3x squared plus y squared minus 2y squared, all over that denominator squared. So that's 4 plus 3x squared plus y squared squared. And we can combine up those like terms here. We have y squared minus 2y squared for a beautiful final answer of 4 plus 3x squared minus y squared. And that's all divided by the denominator squared. So we have 4 plus 3x squared plus y squared squared. And again, make note that in the numerator we have that minus y squared. In the denominator you have a plus y squared. So these are not like terms. If it helps, you can even incorporate parentheses around your numerator. And we're all set. Last but not least here, we want to go ahead and find the partial derivative for the h component with respect to z. So our h component is z, and that's all still divided by 4 plus 3x squared plus y squared. And what's nice here, again, we want to find the partial derivative of h with respect to z. And so notice if we look at this component, we only have one z here. It's in the numerator. So that denominator is just a constant. So we're left here using just the power rule. The partial derivative of h with respect to z is just 1 all over 4 plus 3x squared plus y squared. And we're all set. So we have the partial derivative of f with respect to x. We have the partial derivative of g with respect to y. And we now have the partial derivative of h with respect to z. So the only thing with this is we don't want to get so excited we found these partial derivatives that we forget our job here is to find the divergence. So we're going to need to take the sum of these three partial derivatives. And before we do that, notice here, since we're taking the sum, notice that the partial derivative of f with respect to x and the partial derivative of g with respect to y have the same denominator. So we are going to want to go ahead and convert the h component, the partial derivative of h with respect to z, so that it too has that same denominator. So here we go. I'll scroll up for more room once we write these down. So we want to now compute the divergence, or calculate the divergence. And we of course know that's the partial derivative of f with respect to x, plus the partial derivative of g with respect to y, plus the partial derivative of h with respect to z. So taking what we just found, we have the divergence of the vector field is going to be equal to 4 minus 3x squared plus y squared, and that's all divided by 4 plus 3x squared plus y squared squared. And now we're adding the partial derivative of g with respect to y, which will be 4 plus 3x squared minus y squared, and that's all 2 divided by 4 plus 3x squared plus y squared squared. And now last but not least, we want to add the partial derivative of h with respect to z. And what I'm going to do is get that common denominator here. So we can think about multiplying this partial derivative, the numerator and denominator, by 4 plus 3x squared plus y squared. So that this term, this partial derivative, will match or have the same denominator as the other two. So this is going to be plus 4 plus 3x squared plus y squared, all divided by 4 plus 3x squared plus y squared squared. Phew! So we've got it. We've got our divergence here. And we need to, of course, simplify this. And now that everything has that same denominator, we can simply rewrite this as 4 minus 3x squared plus y squared plus 4 plus 3x squared minus y squared plus 4 plus 3x squared plus y squared, all over that one happy denominator of 4 plus 3x squared plus y squared squared. And we can simplify. So let's see, we have these three constants that we can add together. We also see that we have this minus 3x squared and a positive 3x squared. So those guys cancel each other right out to 0. We have this minus, or the positive y squared and a minus y squared. That will cancel each other right out. And so our final answer here is going to be, we have 4 plus 4 plus 4, which is 12, plus 3x squared plus y squared. And this is all divided by 4 plus 3x squared plus y squared squared. And so this is our beautiful final answer here for the divergence of the vector field.